Now, if we consider Newton's third law, so Newton's third law states that two objects must experience a force F of the same magnitude but in opposite directions. Now, let's have a look at Newton's law of gravitation. So, Newton's law of gravitation states that the force between 2-point masses is directly proportional to the product of the masses. So, in this case, it's m1 times m2. It is inversely proportional to the separation squared. So let's just say that you've got 2-point masses, they're separated by a distance r, then you square that distance. And there's a constant of proportionality. In this case, the constant of proportionality is g, and it is 6.67 times 10 to the minus 11. This g is not equal to 9.81, and because A can vary, right? Because G is 9.81, but this G varies. This G can vary on a different planet. For this big G, it is the gravitational constant rather than the gravitational field strength of the Earth. So this big G is the gravitational constant, and the small g is the gravitational field strength. And the gravitational field strength on the Earth is 9.81, and remember that it has the units of meters per second squared, or remember the equation G equals F over m, so it's newtons per kilogram. Right, so going back to Newton's law of gravitation, so F, the force, is equal to minus G times m1 times m2, all divided by r squared. And let's just compare this with Coulomb's law. Remember, Coulomb's law is K, which is 9 times 10 to the 9, times Q1 times Q2, all divided by r squared. Now, why is it minus, you ask? Well, if you have the charge, if you have one of the charges is positive and the other charge is negative, they will attract. And the overall force is negative, because anything positive times anything negative will give you a negative. So that's why the force is negative. And that means that if you have a negative, that implies attraction. So following from that rule, the minus implies it is attractive. So anything that is gravitationally attractive, it would mean that it is not repulsive, meaning it will go towards the center of the object. So gravity is always attractive. You don't, anything with mass, you don't see anything that's repelling, but that will go into dark matter, and that does not, it's not relating to this right now. Right, so it's negative. The negative means that it is attractive, because by convention, if you have a positive and negative charge, when you multiply them together, you get a negative. So that's why there's a negative there. And masses are usually positive, and r is usually positive, and because you're squaring it, you get a positive answer. Alright. What happens if you have three objects? So if you have object A, object B, and object C, now if you're just focusing on object A, object B is pulling on object A, and object C is pulling on object A. If you focus on object B, A is pulling on B, and C is pulling on B. So it's like a tug of war. One's going negative, one's going positive. If you focus on object C, objects A and B are pulling object C to the left. So if you look at the yellow box at the bottom, for mass A, mass B and mass C is pulling on it. So in this case, F brackets AB, meaning the force between the two masses AB, and F brackets AC, meaning the force is between A and C. So for mass A, it is the force between A and B, and it is B pulling A, and F brackets AC, it is the force between A and C. In this case, because it's going to the right, that's why it's positive. So if you're just focusing on mass A, it is the total of the forces from A and B and A and C. For mass B, you can see that mass A is pulling on mass B to the left. That's why there's a minus F brackets AB. And then you need to add on the positive, the forces between B and C. And that's why you have a positive F brackets BC. For mass C, it is going to the left. So if you look at the if you focus on mass C, the forces between A and C will be negative F brackets AC, and it's going to the left. And again, focusing on object C, the forces between B and C is again negative, and that's why it is minus F brackets BC. Let's have a look at this slide. So the force F is exerted on mass M towards mass M2 and mass 2 towards mass M1. So again, this is Newton's third law, and they're pulling on each other with the same magnitude. So M1, the mass M1 is pulling the mass M2 with a force, and mass M2 is pulling mass M1 with a force, and they are the same forces, the same magnitude. The force F is weaker if the distance r is further away from each other. So if the distance between M1 and M2 is increasing, so if the distance between them is higher, if the distance is longer, then the force is weaker. So for example, if the distance between them is twice as long, then the forces between them will be 4 times weaker. On Earth, Earth's gravity affects all objects. If M1 is Earth, then we call F affecting M2 as the weight of M2. And gravity is not the only force. More than one force can affect an object. The object is accelerated according to the sum of the forces affecting it. So this is just the resultant forces, F equals ma, where F is the resultant force. Let's move on to this slide. So for this slide, you have a graph of force against R. In this case, it's positive, but it is actually negative. But we're doing it positive just to make it easier. If it was negative, then obviously the graph will be reflected on the x-axis. So here you have F against R, and it is a curve. It's not a straight line, because the variable is R squared. So this is the graph of force against distance. Now, if you look at this graph, this is F against 1 over R squared. Now, if you have F over 1 over R squared, assuming that M1 and M2 are constants, and you know that G is a constant, you're going to get a straight line. Because if you compare F with Y and X with 1 over R squared, you get a negative gradient. So the gradient here in this case would be minus G, which is 6.67 times 10 to the minus 11, and multiply that by M1 and M2.